Good morning. Today, previously I have just given the introduction of discrete Fourier transform. Now let me say you a little bit about discrete Fourier transform. Actually, what is Fourier series? What does it represent basically? It is known that Fourier series is used to represent a repetitive periodic signal, and the spectral values are discrete in the frequency domain. Okay, is it clear? Now, what about Fourier transform? The Fourier transform gives the frequency domain representation of a non-periodic signal whose frequency response is continuous, and this transform is our continuous Fourier transform, or in short we call it CFT. CFT. Yeah? The Fourier transform of a discrete time signal is a continuous function of frequency. Such a continuous frequency spectrum is not suited at all for digital signal processing. So to facilitate this, the discrete time signal has been represented by samples of its continuous frequency spectrum. The continuous frequency spectrum, it is having certain samples, it is divided into certain samples, and it has been represented for illustrating the discrete time signal. This frequency domain sampling leads to what we call discrete Fourier transform, or DFT, Though discrete time Fourier transform is defined for both finite and infinite sequences, DFT is applicable to finite length sequences only, and DFT itself is a sequence. So we can say that DFT is a very powerful computational tool for performing frequency analysis of discrete time signals. Usually, a general purpose digital computer or a specially designed digital hardware is used for DFT computation, or to find DFT, we use a specially designed digital signal processor. Listen very carefully. So DFT, what is its use? What does it determine? DFT determines the frequency content of a signal. It determines the frequency content of a signal containing frequency, a signal comprising of frequency is measured by DFT. It is also used to perform linear filtering operations in the frequency domain. It is also used for what? For filtering operations, certain filtering operations, linear filtering operations in frequency domain. Clear? Now, if we consider a periodic discrete time signal, then the discrete Fourier transform can be defined as a finite duration discrete frequency sequence obtained by sampling one period of Fourier transform. So, if Xn is a finite duration sequence, then discrete Fourier transform of the sequence is given by a particular mathematical formula. Now I'll be sharing the screen so that all of you can see the mathematical formula and understand better. Let me share. Just wait a while. Just a little bit. Please wait. It is opening up. Yes, it is opened. Now you see here, the Fourier transform, discrete Fourier transform is defined like, of the sequence is this: xk is equal to summation n equal to 0 to n minus 1 xn into e to the power minus j 2 pi k into small n. It's not suffix n, it's k into small n divided by capital N. Now what is this capital N? Capital N is the number of samples. If there are n samples in the frequency spectrum, then we call it a n point DFT. I'm repeating again. If there are n samples, capital N denotes the number of samples. So if there are n samples in the frequency spectrum, then the DFT will be called a n point DFT. Is it clear? Now, what is k? K is a constant basically, which is equal to 0, 1, 2. You can see I've denoted it like this, up to n minus 1. It is taken up to n minus 1. Now, if we summarize the formula of DFT, then capital X of k gives you summation of n equal to 0 to n minus 1 xn into w suffix capital N to the power kn. Where does it come? This w suffix capital N to the power kn is nothing but the denotion of e to the power minus j 2 pi kn by capital N. You can see I've written underneath where wn to the power kn is equal to e to the power minus j 2 pi kn by capital N. Clear? Listen very carefully. Now, what is wn? All of you might ask, what is wn? I'll be coming it to a bit later because it has got a specific meaning. It has got a specific thing to make you understand. So I'll be coming it to a bit later. Now, just the inverse, like we have done in Z transform, we have found out Z transform, and again we have found out the inverse of transform. Any transformation has its inverse, like you have done in circuit theory, Laplace transform, and again you have computed, you have found out the inverse Laplace transform also, isn't it? Likewise, you have done in DSP Z transform, the previous chapter that I have discussed. There, the inverse Z transform also you have seen using partial fraction expansion, residue method, convolution method, long division method. These all are the methods to find out, compute the inverse Z transform. Likewise, inverse DFT, inverse discrete Fourier transform, will be xn, because your xn is the sequence, is the signal. Xk is the sampled and the DFT value. So here your xn will be your output and your xk, the DFT, will be inside the formula. So xn is equal to 1 by n summation k equal to 0 to n minus 1. In our DFT formula, we have n equal to 0 to n minus 1. Here you have k equal to 0 to n minus 1. Note down the difference. No need to memorize the formula. You see the difference of the formula, you will be memorizing it by yourself. You will be knowing it by yourself, you will be learning it by yourself. So k equal to 0 to n minus 1, x of k e to the power j 2 pi kn by n. Mind it, when you wrote the DFT formula, it was x of n e to the power minus j 2 pi kn by n. Now here it is e to the power j 2 pi kn by n. And this also denoted by wn to the power minus kn. Here wn to the power minus kn, if you see previously while writing the DFT formula, wn to the power kn, if it is e to the power minus j 2 pi kn by n, where n is the number of samples, capital N, find it. So in case of inverse DFT, it will be obviously Wn to the power minus k, because e to the power plus j2 pi kn by capital N. The symbols are having the usual meanings. Here in the previous, while finding out the DFT, here k was equal to 0, 1, 2 up to n minus 1. Now here small n is equal to 0, 1, 2 up to n minus 1. Clear? Now to illustrate this, we have found out, I have given a simple example for you to find out the DFT of the sequence xn equal to half. It's a time-wise signal, like xn equal to half, where n is greater than equal to 0, less than equal to 2. Or if xn equal to 0 at otherwise any value of n, at any other value of n. So how will you find the DFT? What do you think? The DFT formula, you will be putting the basic formula of DFT. So what does the basic formula of DFT say? Go back to the basic formula of DFT. Xk equal to, I'm telling it slowly so that you can understand clearly. Xk equal to summation of n equal to 0 to n minus 1 xn into wn to the power kn. Come down again to the problem. You see, summation xk equal to summation n equal to 0 to n minus 1 xn e to the power minus j2 pi kn by n, that which is our w suffix capital N to the power kn. Now here you see the value of n is between 0 and 2, means it has touched the 0 value, it has touched the second value also. So we have to take the value of 0 also, we have to take the value of 2 also, isn't it? That means our n minus 1, the upper limit of the summation formula, n minus 1 will be equal to 2, which implies our number of samples equal to 3. Clear? Capital N is the number of samples. So number of samples equal to 3. So therefore, adjusting the formula, you write summation n equal to 0 to 2 xn e to the power minus j 2 pi kn by n. Let me go to the next page. Now you see, it was xn, right? So if it is xn, then n stands for 0 to 2. So it will be x0 e to the power minus j0 plus x1 e to the power minus j2 pi k by n plus x2 e to the power minus j 4 pi k by n. Clear up to this? Now e to the power 0 is 1, anything to the power 0 is 1. So x0, x of 0 is half, plus magnitude will be half, obviously, because the xn is half for n equal to 0 to 2. So obviously the magnitude in each case will be half. So half plus half into e to the power minus j 2 pi k by n plus half into e to the power minus j 4 pi k by n. Why it's 4 pi k by n? Can you say? Because you see, the original formula is e to the power minus j 2 pi k into small n by capital N. So if you replace small n by 1, you get minus j2 pi k by n in this case. If you replace small n by 2, you get minus j 4 pi k by n. Am I clear? So this gives you the second line. Now come to the third line. Take half common. It's very simple basically. Just take half common from all the three terms. 1 plus this. Now this one, e to the power minus j 4 pi k by n, will be simplifying it into two parts. How and why? First of all, we'll be simplifying it into two parts to get e to the power minus j 2 pi k by n. Why we will do it? My question is why we will do it? Why 2 pi k by n? Because there already exists a value e to the power minus j2 pi k by n, so that it's easier for us to take common at the end and conclude the problem. Clear? So we will be defining e to the power minus j4 pi k by n into two parts, which is I have written like this. See, e to the power minus j2 pi k by n divided by e to the power j2 pi k by n. Do you understand? You can see using the methods of exponents, you'll be getting e to the power minus j4 pi k by n. I've just split it, nothing else. Now, along with half, I've taken in this line, I've taken e to the power minus j2 pi k by n common. So what do we get? Here it will be like this. Here it will be 1. The second term will be 1. The first term will be e to the power minus j2 pi k by n, as the first term was 1 here. And the third term will be just the numerator. Clear? Now, 1 plus e to the power minus j2 pi k by n plus e to the power minus j2 pi k by n. What is it? What is it? It is 2 cos 2 pi k by n. Okay. Why? Because I think you have you know the Euler's formula. E to the power j theta. What is it? Cos theta plus j sine theta. So similarly, if you simplify this and this, you'll be getting 2 cos, sine terms will be cancelling, 2 cos, because e to the power minus j 2 pi k by n means cos this plus or minus j this, because this plus, if you get this, then it will be one thing I just would like to tell you, one thing I'd like to tell you. Just wait. This one will be plus. This one will be plus. Clear? So this one will be, you see, it will be plus. It won't be minus, it will be plus. Is it clear? Now is it clear? Now how the sign terms will be cancelling out? Is it clear? Because if you take common, there was a slight mistake in my note. So just get into it. It will be plus e to the power plus j 2 pi k by n plus 1 plus e to the power minus j 2 pi k by n. Like this, you get the sign terms cancelled, and it is 1, it's remaining 1 like it, and 2 cos 2 pi k by capital. Clear? That's all about your DFT simple formula wise doing any problem. Now next we come to a very important thing. Next we come to a very important thing. Let me erase this part again, this plus, because you're seeing the screen and you'll be getting confused. So I've erased it. Yes. Now you get it. So the second part, what we call is the Twiddle factor. Some minutes earlier, I told that I'll be explaining it later on. I'll be explaining it later on. So now I get it, and I'm explaining it to you. You see, what is Twiddle factor? So what is Twiddle factor? Twiddle factor is nothing but a factor. Now, why this factor is used? It is basically a redundancy factor. Twiddle factor is basically a redundancy factor. Now, this factor, you get it from the formula of DFT itself. Now, what is the formula of DFT? Xk equal to summation of n equal to 0 to n minus 1 xn e to the power minus j 2 pi kn by capital, isn't it? Now, previously, I replaced the e to the power minus j 2 pi kn by capital N by w suffix capital N to the power kn. This wn is my Twiddle factor. Is it clear? Not w suffix n to the power kn. Only w suffix n is my Twiddle factor. So, in terms of expressing the Twiddle factor, if I ask you, what is the expression of Twiddle factor? Then what will it be? So, w suffix capital N, where n is the number of samples, is equal to e to the power minus j 2 pi by n. Isn't it? This will be the Twiddle factor. Now, what about the magnitude and phase of Twiddle factor? What about the magnitude and phase of Twiddle factor? What? So before magnitude and phase, can anyone say what kind of a constant factor is Twiddle factor? Twiddle factor is basically a trigonometric constant coefficient that are multiplied by the data in the course of your problem. That are multiplied by the data in the course of your problem. Is it clear? Twiddle factor is a factor that are multiplied by your data in the course of the problem, and it is basically a trigonometric constant. It was coined by Gentleman and Sandy in 1966 in Fourier transform. The Twiddle factor was coined by these two scientists in 1966 in Fourier transform. We use Twiddle factor in both DFT, discrete Fourier transform, as well as in FFT, fast Fourier transform. Clear? Okay. Now come to the magnitude of the Twiddle factor. So what about the magnitude of Twiddle factor? So Twiddle factor is e to the power minus j 2 pi by capital N. So its magnitude will be mod of this, isn't it? Now mod of this, I have written 1. How? Again, that inverse formula you have to repeat, e to the power minus j theta, where theta is 2 pi by capital N. 2 pi by capital N, isn't it? So e to the power minus j theta is cos theta minus j sin theta. That means if you elaborate it, it will be cos of 2 pi by capital N minus j sin of 2 pi by capital N. So that is equal to, mod of that is equal to 1. And the phase angle is the angle of e to the power minus j 2 pi by capital N, which is equal to obviously 2 pi by capital N. That is your angle here, isn't it? So it's very easy. Now, the one thing to note down, please note down all of you, the above magnitude and phase angle values of the Twiddle factor. What does it show? What does it show? Does it show anything? Yes, it shows many things. What does it show? It shows that the Twiddle factor is a vector. There is a vector quantity where it is a vector on the unit circle. It is a vector on the unit circle. And it represents, what does it represent? If it is a vector on the unit circle, then what does it represent? It represents n equally spaced samples. Here n means capital N. number of samples. N equally spaced samples. Clear? Now come to the properties of Twiddle factor. Okay, come to the properties of Twiddle factor. Twiddle factor, basically, there are two properties. One is the periodic property and one is the symmetry property. One is the periodic property, one is the symmetry property. Here, you see, we have considered a circle and we have drawn the two axes, the real axis and the imaginary axis. The real and the imaginary axes are drawn. We have considered a circle and we have taken points. We have taken points where you can see there are many values written for each point. Clear? There are many values written for each point. Now, one quadrant, you see, one quadrant, if this is denoting your 90 degree, then half of this quadrant will be denoting your 45 degree, isn't it? If this quadrant is denoting 90 degree, this is a 90 degree angle, isn't it? It's a right angle. So half of the quadrant, if you partition it, it will be denoting your 45 degree. That's why I've written pi by 4. And this line will also be identical as pi by 4. Here also you can write pi by 4. Clear? Understand slowly. How many points that I have plotted over here? You see 1, 2, 3, 4, 5, 6, 7, 8. There are 8 points. That means there are 8 samples. I've taken 8 samples on this circle. I've taken 8 samples on this circle. N equal to 8. That means my capital N is equal to 8 over here. Here, my capital N is equal to 8 and small r, that is my radius, small r, unit circle. It was a unit circle, remember. So small r, I am considering from 0, 1, up to 16. Small r, I am considering here, it's 0, 1, up to 16 are plotted. You see the plot carefully. Now, seeing the plot, I'll be uploading this in your Google Classroom also. No need to worry. I'm just sharing my screen right now while explaining. It's very difficult to explain on mathematical thing. Yeah. So just listen to it. You see, since there are 8 samples, so we will consider this is a 8-point DFT. Remember, n-point DFT, where n is the number of samples, capital. So here capital N is equal to 8. So this is a 8-point DFT. Clear? 8-point DFT. Now, 8-point DFT means equally spaced samples. I have said already, equally spaced samples. N represents equally spaced samples. So on the real axis, start from here. On the real axis, if I give 8-point DFT, W8 to the power 0, then my next term will be W8 to the power 8. You see, equally spaced. The next term will be W8 to the power 16. Clear? And its value is 1. And its value is 1. Is it clear? Clear? Now, go clockwise. W8 to the power 1, the next sample. W8 to the power 1. 1 means here R equal to 1. I've taken R equal to 1 here. So if I've taken R equal to 1 here, then the next term will be R equal to 9. And this is equal to e to the power minus j pi by 4. Okay, which gives you the value 1 by root 2 minus j by root 2. Clear? Third point, clockwise third point, W8 to the power 2, which gives you equal to the second point will be W8 to the power how much? 10, which is equal to minus j. Minus j. Fourth point, W8 to the power 11. So it is coming from that side. This is starting. So it will be 2 plus 8, you get 10. 1 plus 8, you get 9. 0 plus 8, you get 8. So here it will be 11 minus 8, you get 3. Because it is coming from that side. So that's why I've given dotted sign previously in all these side values. So it is minus 1 by root 2 and minus j by root 2. You understand? Minus j by root 2. It's just the opposite. Very simple it is. So minus 1 by root 2 and minus j by root 2. You get here 1 by root 2 and minus j by root 2. The fifth point, I hope it's the fifth, isn't it? 1, 2, 3, 4, fifth. The fifth sample rather than you can say in clockwise direction. It gives you the W8 means the 8-point DFT, W8 to the power 12, and you minus 8, it gives you W8 to the power 4. So 12 minus 8, you get 4. Here in the real axis sign, it is 1. So the value will be minus 1. Similarly, W8 to the power 13 minus 8 gives you W8 to the power 5 for this sample. Here it is minus 1 by root 2 plus j by root 2. On the imaginary axis, W8 to the power 6. Again, in the forward path, it will be plus 8. So 6 plus 8 gives you 14. Now, since this value is minus j, so this value you see it's plus j. Correlate like this, no need to memorize. So W8 to the power 7, the last point, equal to W8 to the power 15. And since these two both are negative, and here it's both is positive, 1 by root 2 plus j by root 2. Here, so I've shared this screen. Now wait a minute, I'll be moving on to the next one. You see, the various values are written here, and I have clearly written the values of Wn to the power nk equal to Wn to the power r for r equal to 0 to 16, and for n equal to 8 means that it's a 8-point DFT, and there are 8 samples. So the values are written here identically. Now, in general, what can we write? In general, we can write W to the power r is equal to W to the power r plus minus capital N equal to W to the power r plus minus 2n, which is going on. So this is the periodicity property of Twiddle factor. Okay, it is a periodicity property of Twiddle factor. And next, if you go through the symmetry property, it's very easy because it is almost related to the periodicity property. You see, W8 to the power 1, for example, if we take W8 to the power 1, then what is the value? It's 1 by root 2 minus j by root 2. I've written it, clear? W8 to the power 5, what is the value? It's minus 1 by root 2 plus j by root 2. Okay, so W8 to the power 1, W8 to the power 5. Also, W8 to the power 2 means when r equal to 2, it's minus j. And W8 to the power 6 means when r equal to 6, then it is plus j. See. So, likewise, if the values are arranged, then we can say that W to the power r gives you minus of W to the power r plus minus capital N by 2. And this property is nothing but our symmetry property of Twiddle factor. So there are two properties I have discussed right now. One is a periodicity of Twiddle factor, one is a symmetry property of Twiddle factor. Try to understand. Okay. Now, using this, or may not be using this, basically, we will be doing a problem again on DFT. So, what does the problem say? And look here. What does the problem say? It says that find the DFT of the sequence xn equal to 0, 1, 2, 3. So how many samples are here? There are 4 samples because k equal to 0, 1 up to n minus 1. Now here n minus 1 equal to 3. So n equal to 4. Isn't it? Now xk equal to n equal to 0 to 3. Summation of n equal to 0 to 3. xn e to the power minus j 2 pi kn by capital N. It is not a example of Twiddle factor. It is just an example of ordinary DFT sequence. I just showed how to find the DFT because these problems are very important basically. So n equal to 0 to 3 xn e to the power minus j 2 pi kn by capital N gives you x of 0 e to the power 0 plus, like the previous problem that we have done, it's almost same, x of 1 e to the power minus j 2 pi k by 4 plus x of 2 e to the power minus j 4 pi k by 4 plus x of 3 e to the power minus j 6 pi k by 4. N equal to 4, so denominator will be 4 all through. And in the numerator, the values are changing. So at k equal to 0, what will be x0? At k equal to 0, x0 will be simply 0 plus 1 plus 2 plus 3 for each time. So it will be totally will be coming as 6. Now for k equal to 1, x of 1 will be 0 plus 1 into e to the power minus j pi by 2 plus 2 into e to the power minus j pi plus 3 into e to the power minus j 3 by 2 pi. So 0 will be 0 obviously. 1 into e to the power minus j pi by 2 will be minus j. 2 into e to the power minus j pi will be minus 2. And this will be j3. Okay. So it gives you minus 2 plus j2. Likewise, at k equal to 2, x2 equal to 0 plus 1 into e to the power minus j pi plus 2 into e to the power minus j2 pi plus 3 into e to the power minus j3 pi gives you minus 1 plus 2 minus 3, which is minus 2. And x3 at k equal to 3 x3, similarly 0 plus 1 into e to the power minus j3 pi by 2 plus 2 into e to the power minus j3 pi plus 3 into e to the power minus j3 pi, which gives you minus 2 minus 2j. So final DFT of the sequence of the 4-point DFT sequence gives you xk equal to, from starting you have to write the values. The first value is 6, second value is minus 2 plus j2, third value is minus 2, fourth value is minus 2 minus j2. So I've written like this. So this is the DFT of the sequence xn equal to 0, 1, 2, 3. Thank you for today.